Good afternoon, everyone. Thank you all for joining this presentation. My name is Sina Shalom, and today I'll be presenting our work on models and mechanisms for spatial data processing. This is an approach for achieving individual fairness for location data. I'll be presenting this work on behalf of the other authors, Professor Gabriel Anita and Professor Cyrus Shahabi. We'll start the presentation by providing some background information, talking about the location bias and unfairness, the fairness metric that we have, the proposed method, and ultimately the experimental results and conclusion. So ML classifiers are everywhere and used for social good. These including the applications such as loan approval, assessing credit worthiness of a person, and deciding about the insurance premium. The initial belief was more information that we have, better the decisions, but this realization was soon challenged as bias manifested in data, and the classifiers were having these discriminatory outcomes with respect to sensitive information. Sensitive information are things such as gender, race, and religion. These are decided usually by different organizations and governments. So the initial attempt on resolving this problem was completely removing the sensitive data from the features to the ML models. This helped to a certain extent, but the problem is they are usually correlated with other features. That's why more advanced algorithms were required. So these algorithms come into different parts of the ML pipeline from pre-processing, in-processing, and post-processing approach. One vital source of information that's missing in the literature is the location information and data of users. The reason they are important is that they are highly correlated with race and credit patterns, housing, and other uh, information regarding to elections. Uh, they also have more complex key identifiers. They could come in different dimensionalities, include things such as zip codes, neighborhoods, and the coordinates of users. Before we move on to the methodology of the presentation, let us start by discussing the fairness metric that we have. Broadly speaking, fairness metrics could be categorized into two groups. The first one is group fairness metrics, where the goal is to have uh, some sort of a statistical metric statistical metric across groups in the society and in the classifier. Some of the key metrics include statistical parity, equalized odds, and equalized opportunity. The second group is called individual fairness. Here, our aim is to achieve fairness on the individual level, and with one of the key principles being treating similar individuals similarly. Individual fairness addresses some of the limitations that we have for the group fairness, and in general is a stricter metric. The definition that we use here is as follows. The goal is that for every two individual ui and uj, we want some sort of distribution distance between their scores to be less than or equal to their similarity. Let's now try to formulate the problem of fairness and bias for location information. So we derive the definition of location bias from the original definition of bias in machine learning, and it goes as follows. This is defined as distortion or algorithmic bias generated based on locations of entities in the geospatial domain or their distances to reference point, and we refer to them as location bias. So bias is the source of unfairness. Note that we are distinguishing between two key factors. One is that the distance between a reference point, and the second part is just geospatial domain, meaning that having the dimensions, having the locations in a higher dimensions. And we do that due to different applications that each one has. The problem that we aim to solve in this paper and presentation is as follows. Let us have the locations of users as L1 to Lm. Each one of them is a metric in the, with k dimensions. And We want to classify them over the output set A. In our case, the output set is a binary classifier, so the values are 0 or 1. And we have this randomized mapping demonstrating the classifier M that goes from L to our output space. And we say it satisfies individual spatial fairness if and only for every two locations. We have their statistical distribution distance MLI minus MLJ in absolute value to be less than or equal to the norm of the difference between locations. So this is the distance between two users. So as I mentioned before, we distinguish between the 1D case with higher dimension. We call the first one distance-based fairness. This is the one that we try to look into the distances to a particular reference point. The common way it comes up is in a nearest neighbor domain, like KNN. We try to have this closeness to a particular reference point in that example. Uh, and the second one is called zone-based fairness. These are the ones on higher dimension, meaning that you have the coordinates. And some of the applications include gerrymandering, assigning loan to different neighborhoods, so on and so forth. So here, if two houses are, for as an example in an insurance premium example, if you have two houses close to each other, you want to have more or less similar insurance premium for each one of them. We do not want to be in the scenario with when the sudden change in the boundaries is causing very different outcomes for the houses. Some of the key challenges that we face in applying individual fairness for location data is as follows. For every two individual, we have to achieve these constraints. So we have this quadratic complexity, and people usually come up with a utility function and aim to apply that quadratic number of constraints on the utility function, which is quite complex for lots of location data. So we seek this more practical mechanism to apply it and achieve individual fairness for location data. The key idea behind our approach for achieving individual fairness is called Seefer polynomials. Let us illustrate Seefer polynomials based on an example. Here in the image, you could see a landmark, and it's an advertising scenario where you want to have a hiring decision or have this housing advertisement that we want to show to people. And let's say we have this individual A to D on the map. If we have a strict perimeter that we want to only for showing this advertisement, even though two individuals A and B are pretty close to each other, if one of them is in the perimeter and is going to receive that advertisement and the other one has zero chance of receiving that. And the idea is, can we somehow make this scenario fairer by giving some sort of a statistical probability to each one receiving the advertisement. Let us record this information as users, their coordinates, distance reference point, and we would have other features as well. And we have this classifier that gives us the likelihood of a person seeing that advertisement. The way we try to achieve individual fairness is as follows. Let us have on the x-axis the distances to this reference point, this particular landmark, and on the y-axis their scores. The idea is that can we come up with a polynomial that when we feed this data to that particular polynomial, that polynomial by itself has this characteristic of individual fairness. So we are sacrificing some utility, but at the same time we are ensuring that the result is C-fair. Here this C is a tuning parameter for allowing us some room to ease the fairness assumption. One example of C-fair polynomial is C times x to the power of n over n, where we prove in the paper that by triangle inequality we could show that indeed this gives us C-fairness. But the idea is to have this polynomial that we have the minimum amount of sacrifice in our utility. So therefore, the question is how to actually learn these polynomials, how to know their coefficient. For different scenarios, different dimensionalities, uh, and coordinates, so on and so forth, we come up with a sufficiency condition for a polynomial to be C-fair, right? We prove these different theorems in the paper. Then, based on the information that we have over the locations, we vectorize the problem, write write them in the optimization format, and ultimately we figure out the degree of the polynomial. Here is a table for different data dimensionality, the norm of data that we have, and polynomial order, and we provide the sufficiency conditions based on the theorem numbers. Uh, Let us go through an example based on that one polynomial that we discussed. For every location we input it into the polynomial, we vectorize them and have a matrix of all those coefficients and the corresponding scores, and then we write this minimization form. Note that the number of uh, constraints that we have in the optimization now is n plus 1, as opposed to previous way that the individual fairness being achieved by select 2 from n. So it's linear, no longer quadratic. And the error is the degree of polynomial is decided based on a heuristic approach and minimizing the error from data. Let us now move on to the experimental results. We have different data sets and apply an approach on different data set and applications. But here I have an example for assigning the allocating budget to different police departments in Chicago. We overlay this 1000 by 1000 grid on top of the Chicago map. And we consider different crime categories. We train a model, logistic regression model, to determine the likelihood of a crime being happening in a particular grid cell. And the idea is that how to do these budget allocations in a fair way. So here for different values of C and having two dimensions, as we are in, we have the coordinates, we are in two dimensions. You could see the plots for each one of them, C values, showing the loss in utility and the percentage of unfairness on the y-axis. Uh, Compared to the benchmark, you could see we could achieve much higher levels of unfairness with similar uh, amount of loss in utility. Note that changing the degree of the polynomial and adding variables will have the flexibility of moving around in this graph. Here I have the percentage of unfairness versus utility for distance-based mechanism and zone-based mechanism. We could observe that higher the amount of loss, better the percentage of unfairness which we could achieve. This is essentially the fairness utility trade-off. By that, I would like to conclude the presentation. We explored individual fairness for location data. We talked about the two key approach, which are distance-based fairness and zone-based fairness. We had our key solution, fair polynomials, and the broader implication of what we have is that this method could be applied for achieving individual fairness for other scenarios. The key future direction that we aim to explore is having more complex spatial queries. By that, I would like to thank all of you for listening to this presentation, and I look forward to any questions you may have.